On Mars, there's a volcano so massive that if you were standing at its base, you wouldn't even be able to see the summit. The peak would be hidden beyond the curve of the planet itself. This single mountain covers an area roughly the size of Italy and stands nearly 3 times taller than Mount Everest. But Mars is a smaller, quieter planet than Earth. So how did it end up with the largest volcano in the entire solar system? The answer reveals a fundamental difference in how planets work, a story of a cosmic construction project that lasted for an almost unimaginable amount of time. The volcano is Olympus Mons, and its sheer existence forces us to reconsider the rules of geology. For centuries, we didn't even know it was a mountain. 19th century astronomers spotted a bright, enigmatic patch they named Nix Olympica, or the snows of Olympus, but it's true, staggering nature wasn't confirmed until the Mariner 9 probe arrived in 1971. As a global dust storm on Mars finally began to settle, the first things to emerge from the haze were the tops of colossal volcanoes, with Olympus Mons reigning supreme. But here's the strange part: it may look like a mountain, but it was built more like a giant, slow-moving flood of lava, layer by agonizing layer. So how does a volcano get this big? And why did Mars create something Earth simply couldn't? The Earth comparison, our restless planet. To get why Olympus Mons is a uniquely Martian feature, we first have to look at home. Earth is a geologically restless world. Its surface is broken up into massive tectonic plates that are constantly, slowly, grinding against, pulling apart, and sliding under one another. This process, plate tectonics, is the engine behind our planet's most dramatic features: our sprawling mountain ranges, deep ocean trenches, and, of course, our volcanoes. Most of Earth's volcanoes pop up at the boundaries of these plates, like the famous Ring of Fire around the Pacific Ocean. But there's another type of volcano that gives us the perfect comparison for Mars: the hotspot volcano. Think of the Hawaiian Islands. Deep beneath the Pacific Plate, there's a stationary plume of superheated rock, a hotspot that punches through the crust to form volcanoes. But here's the key difference. The Pacific Plate is always moving, drifting over this hotspot like a conveyor belt. As the plate moves, the hotspot creates a new volcano, then the plate inches along, and another one forms in a new spot. This is how the long chain of islands and undersea mountains we see today was created. The oldest islands, like Kauai, are volcanically dead because the plate has carried them far away from their magma source. The youngest, the Big Island, is still active because it's currently parked right over the hotspot. This constant movement means no single volcano on Earth can just keep growing forever. It gets cut off from its fuel, and a new one starts up somewhere else. Our planet's restlessness, the very thing that makes it so dynamic, puts a strict size limit on its volcanoes. The Mars difference, a world standing still. Mars, on the other hand, plays by a completely different set of rules. The biggest reason Olympus Mons got so huge is what Mars lacks: active, global plate tectonics. Because Mars is smaller, it cooled down faster than Earth, and its crust solidified into a single, largely static shell. It just doesn't have that same system of moving plates. And that had a profound consequence. When a magma hotspot formed in the Martian mantle, the crust above it didn't move. Instead of a conveyor belt creating a chain of smaller volcanoes, the hotspot acted like a cosmic blowtorch aimed at the exact same spot for an immense period of time. For hundreds of millions of years, lava could pour out from the same vents, building one single, monolithic structure. Layer after layer of lava flowed out, piling on top of the last, allowing the volcano to grow relentlessly and uninterrupted. That explains the how, but there's another crucial factor that allowed Olympus Mons to get so tall: gravity. The surface gravity on Mars is only about 38% of Earth's. On our planet, a mountain's height is ultimately limited by its own weight. If a volcano grew as tall as Olympus Mons here, the crushing gravitational pressure would cause it to collapse under its own mass. But on Mars, with its weaker gravity, that same rock weighs far less. This lower pull meant the volcanic structure could be built higher and wider, reaching an incredible elevation of nearly 22 kilometers, about 14 miles, without caving in on itself. The combination of a static crust and low gravity was the perfect recipe for a megavolcano. If you're enjoying these deep dives into the wonders of our solar system, do me a favor and like this video. It tells the algorithm you value curiosity-driven science, and it helps more people discover just how strange and magnificent other planets can be. And trust me, the story of this mountain gets even bigger. The perfect storm of volcanic growth, the lack of plate tectonics, and lower gravity are the main characters in this story, but they weren't working alone. A perfect storm of 4 distinct geological conditions came together to build this monument. First, as we've seen, was the mostly stationary crust over a magma hotspot, which gave it a stable foundation for an epic period of construction. Second was the low gravity, which allowed the structure to grow to a height that would be physically impossible on Earth. The third ingredient was the lava itself. Olympus Mons is a shield volcano, which means it wasn't formed by violent, explosive eruptions. Instead, it was built by extremely fluid, runny basaltic lava. Think less of a thick paste and more of a watery, syrupy consistency. This low viscosity lava could travel for huge distances before it cooled, creating the volcano's distinct shape, not a steep, pointy cone, but an incredibly broad, gently sloping shield. The average slope on the flanks of Olympus Mons is only about 5 degrees. It's so gradual that if you were walking up it, it would feel less like climbing a mountain and more like a long, persistent uphill walk across a plain. The fourth and final factor is preservation. On Earth, even our biggest mountains are under constant attack from wind, rain, ice, and rivers, which relentlessly wear them down. Mars, on the other hand, has a very thin, dry atmosphere and no liquid water on its surface today. That means there's very little erosion. So Olympus Mons, having formed over eons, has been left almost perfectly preserved, a snapshot of Martian geology frozen in time. Based on crater counting models, scientists estimate that some of its most recent eruptions may have happened as recently as 25 million years ago. Some lava flows even appear to be as young as just 2 million years old, suggesting the volcano may not be totally extinct, but merely dormant. The broader implications: a planet-tilting giant Olympus Mons isn't just a big mountain, it's a feature so massive it may have literally reshaped the planet. It sits on the edge of the Tharsis Bulge, a huge volcanic plateau home to several other giant volcanoes. This region is so immense and heavy that many scientists believe its formation caused the entire outer crust and mantle of Mars to slip and rotate, possibly tipping the planet's axis by about 20 degrees some 3 billion years ago. Imagine a weight so great it causes the whole outer shell of a world to shift. That's the scale we're talking about. For scientists, the volcano is an invaluable archive. Each of its thousands of lava flows is like a page in a history book, recording the chemistry of the Martian mantle at different points in time. The 6 overlapping calderas at its summit, giant craters formed when the magma chamber roof collapsed after eruptions, tell a story of multiple pulses of activity over millions of years. By studying these features, geologists can piece together the long, complex volcanic history of Mars. This is also why Olympus Mons is a tantalizing target for future exploration. Landing there would be a challenge because of the high altitude, but the scientific payoff would be immense. Samples drilled from its flanks could provide a definitive timeline of Martian volcanism and clues about the planet's internal heat. In a surprising twist, recent studies have even detected thin layers of water ice frost that form on its summit during the cold Martian mornings, adding another layer of mystery to this giant. Olympus Mons isn't just a relic of the past, it's an active laboratory for understanding how worlds like ours work. So, why does Mars have a volcano the size of a country? Because Mars isn't Earth. It's a world where a largely stationary crust allowed a single volcanic hotspot to pour lava onto one spot for an incredible amount of time. It's a world where weaker gravity allowed that mountain of lava to grow to a scale our minds can barely comprehend. And it's a world where a thin, cold atmosphere preserved that creation in stunning detail. Olympus Mons forces us to change our perspective. It stands as a silent, colossal testament to the fact that the geological rules we know on Earth are not universal. It's a reminder that the universe can build landscapes far grander and more alien than we can imagine. This isn't a mountain you could climb in a day, it's a planetary feature you would have to traverse for weeks. The next time you look at an image of the red planet, remember that it's more than just a dusty desert. It's the home of a volcano so vast it redefines what a mountain can be, a symbol of a planet with a deep, powerful, and vastly different history than our own. What do you find more mind-blowing, the sheer height of Olympus Mons, or the fact that it grew in one spot for so long? Let me know in the comments below. And if you want more stories that expand your view of the cosmos, make sure you subscribe and hit the notification bell. Stay curious.